Page 149, number 19. A swimming pool is 40 feet long and 20 feet wide, 4 feet deep at the shallow end and 9 feet deep at the deep end. Water is being pumped into the pool at 10 cubic feet per minute, and there is 4 feet of water at the deep end. That's here. Here's the deep end right here. There's 4 feet of water here. So this length is 4. Part A, what percentage of the pool is filled when h equals 4, when the height here is 4, when the height of water is 4. Alright, well this part A does not require any calculus. It just requires some volume calculations. We're going to calculate the volume of the swimming pool and the volume of the water at the bottom of the pool, this shaded area, and we'll form the ratio of the volume of the water divided by the volume of the pool to get the percentage filled. Alright, let's do the volume of the pool first. Notice the shape of the swimming pool. We have the swimming pool is made up of a solid rectangle above the dotted line, this dotted line, and a right triangle, a thickened right triangle below the dotted line. That's actually called, it's a type of cylinder where the base, rather than being a circle, is a right triangle. It's a type of cylinder. Alright, so let's look at the upper part of the swimming pool, that solid rectangle, and we'll just multiply the dimensions. Alright, well, here are the dimensions. The 4 feet here, and if we follow through the dotted line, that's 4 feet. Okay, at the other side as well. So the three dimensions are 4 times 40 times 20. So the volume of the pool is just the product of those dimensions, 4 times 40 times 20. That's 3,200 cubic feet. Okay. Now for the lower part, we have this this triangle, and we'll multiply we'll find first the area of the triangle and multiply that by 20 to get the volume of the lower part. So the area of the triangle is 1/2 the dimension 5. Now where do we get this 5 from? Well, this is 4 because that's the same as the shallow end, and the deep end is 9, so below the dotted line we're left with 5 feet. Okay, for 9 minus 4. Alright, so that would be 1/2 5 times the dotted line, which is 40, times the depth of that figure, or which corresponds to the width of the pool, and that would be 20. Alright, so that comes out to 2,000 cubic feet. So the total volume of the pool is 3,200 plus 2,000, that's 5,200 cubic feet. Alright, now let's look at, sorry, that's the upper part, this is the lower part, let me label that. That's the lower part below the dotted line. Alright, let's look now at the volume of water. Alright, that's another a triangle, a thickened triangle, alright, like we had, similar to the calculation of the lower part of the pool. Okay, so now we're looking at this shaded part here. Here I redrew it over on the right, and we want the area of that shaded rectangle. Alright, so that's going to be 1/2 4 for the vertical dimension. Now the horizontal dimension I labeled x, we have to figure out what that is, times the depth, which is the same as the width of the pool, or 20. So that's the volume of the water when the height of the water is 4. That's the height. To figure out x, we can refer to this diagram, and we have enough information to calculate x because we have some similar triangles. You see this shaded triangle and the triangle that is surrounds it are similar triangles, and we know the dimensions of the larger triangle. All right, so we have a little ratio over here. We have 40:5, a proportion. 40:5 is x:4. Okay, this is 8, so this comes out. So we end up with x equals 32. All right, so this is 32. Okay, and we multiply that out, and the volume of the water is 1,280. So for the percent, we compare the water, the volume of the water, to the volume of the pool. All right, so we have 1,280 divided by 5,200. Okay, that's the water to the volume of the pool, and that's equal to 0.246, or 24.6%. Okay, so now we're ready for part B. Let's go back and read part B. Part B says, at what rate is the water level rising? Okay, that is, at what rate is the water level rising when H equals 4? And let's just remember here we're being told that the water is being pumped into the pool at 10 cubic feet per minute. So that means that the volume of the water is changing. dV dt is equal to 10. All right. Here we have a little calculation of the volume of the water when the height is 4. So let's write down a formula for the volume of the water for a general height. All right, so this is, now we're doing part B, and the volume of the water for a general height h is equal to 1/2 h times x, whatever the length of the water is at the time, well, times 20. The width of the pool stays the same. All right, so that's equal to V. This is all, I'll call this V. Let V be volume of water. And we're going to differentiate both sides with respect to T like we always do. And what we want to figure out is we want to figure out what dH dt is when H is equal to 4. All right, well, what about this variable x? What are we going to do with that? Well, the same thing we did before, except before we use these two triangles, these proportional triangles, or these similar triangles, when H was 4. Let's just draw those same similar triangles, but now let's substitute in a general height of water, height of H. Okay, so here's the larger triangle that goes all the way across the pool. All right, and that represents sort of the slanted part of the pool. And here's the water. All right, we said that below the dotted line the height is 5. This is the entire length of the pool, 40. Let's call the length of the water x, and let's call the height of the water, let's call that h. So the volume of water as the water is being poured into the pool at any time is given by, we have it here, 1/2 hx20 or 10hx. And now let's eliminate x just like we did in the calculation above, using similar triangles, we have a ratio 40:5. We have a proportion here, 40:5 as x is to h. We want to eliminate, this is equal to 8, so we want to eliminate x, so we'll solve for x. So x is equal to 8h. Just cross multiplying over there. And so we're going to put in the 8h right over there. Alright, so let's do that. So we have the volume. Okay, we have the volume is equal to, alright, this is 10 h 8h, or 80h squared. Alright, now it's easy to differentiate with respect to t. Let me bring that up again, just a minute. Let me get that back. Alright, here we are. Let's get dv dt is equal to 80 times 2h times dh dt. And we know that dv dt, the water is being poured in at a constant rate of 10, and now we want to sub in a specific value, h equal 4, because we want to figure out what dh dt is when the height is 4. Alright, so we have 10 is equal to 2 times 80, that's 160, times 4, dh dt. Alright, so then we'll divide by, we'll just divide by 160 times 4, and dh dt is 10 divided by 160 times 4, or 1 divided by 16 times 4, and that comes out to 1/64. And what are the units? Well, the units are feet per minute. H is linear, so we have a linear unit over there, so that's feet per minute.